Look up on a clear southern night. That single, steady point of light low in the constellation Centaurus is not one star, but three, and 4 light-years of empty space stand between you and them. For decades, we believed the brightest two were barren, too restless, too crowded, too drowned in each other's glare to hold worlds. Then, in August 2024, NASA's Webb Telescope quietly recorded an object 10,000 times fainter than its star, and then watched it vanish. Tonight, you are going to travel through layers of discovery, from the naked eye glow of a southern star, through decades of false starts and ghost planets, all the way to a single faint pixel that may be the closest world beyond our solar system ever directly seen, and understand why that pixel changes the meaning of the word neighbor. Before we dive in, if you love exploring nearby worlds and deep space mysteries as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. There is a particular kind of intimacy that attaches itself to the Alpha Centauri system. It is not the intimacy of something well understood. It is the intimacy of proximity, of knowing that something is right there, just beyond your fingertips, and being unable to quite grasp it. For most of recorded human history, people living in the southern hemisphere have looked up at that single brilliant point hovering above the horizon and felt its nearness without being able to measure it. The star has ancient names. The 2 sun-like stars that form the system are called Rigil Kentaurus and Ptolemy. Rigil Kentaurus, Alpha Centauri A, is a yellowish star, slightly more massive than the Sun and about 1.5 times brighter. Ptolemy, Alpha Centauri B, has an orangish hue, a bit less massive and roughly half as bright as our own star. To the unaided eye, they merge into one. To the naked eye, the 2 main components appear to be a single star with an apparent magnitude of negative 0.27. It is the brightest star in the constellation and the 3rd brightest in the night sky, outshone only by Sirius and Canopus. That intimacy, that sense of nearness, is not an illusion. Alpha Centauri AB is the nearest binary star system to the Sun, at a distance of 4.344 light-years. In the vast ledger of interstellar distances, where stars are typically separated by 5, 10, 20, or hundreds of light-years, 4 1/3 light-years is essentially nothing. It is the cosmic equivalent of a house at the end of your street. You can see the lights. You can almost make out the shape of the building, but you cannot yet tell whether anyone is home. This is the central question that has haunted astronomers for generations, and it is the question that NASA's James Webb Space Telescope has now taken its most serious step toward answering. What Webb found, or more precisely, what Webb found and then could not find again, is a story about the limits of human instruments, the patience required by science, and the extraordinary strangeness of searching for worlds around the stars closest to our own. It is a story that begins not with a discovery, but with a problem, not with clarity, but with glare. Pause here for a moment, because the scale matters. When we say that Alpha Centauri is 4.37 light-years away, we are saying that light, the fastest thing in the universe, traveling at roughly 300,000 kilometers every second, takes 4 years and 4 months to cross the distance between our solar system and that one. A radio signal sent from Earth today at the speed of light would arrive at Alpha Centauri in the year 2030. A spacecraft traveling at the speed of the fastest probe humanity had launched at the time, the New Horizons spacecraft, which crossed the orbit of Pluto in 2015, would take roughly 78,000 years to complete the journey. Distance, at this scale, is not merely a number. It is a kind of permanence. It is a wall. And yet, in the context of the galaxy as a whole, which spans roughly 100,000 light-years, this wall is gossamer thin. Alpha Centauri might as well be in the next room. That strange duality, impossibly far by human standards, impossibly close by cosmic ones, is what makes the system so compelling and so frustrating. Astronomers have known since the 19th century that if planets exist anywhere within easy observational reach of Earth, Alpha Centauri is the most promising address. And for most of that time, the hunt for those planets has produced more heartbreak than triumph. To understand why Webb's 2024 observation is so significant, you need to understand the terrain, both the physical terrain of the Alpha Centauri system itself and the historical terrain of the search that preceded it. These two terrains are deeply intertwined, and neither one makes sense without the other. Start with the physical. Alpha Centauri is a triple star system with its two main stars, A and B, together comprising a binary component. Alpha Centauri A and Alpha Centauri B orbit a common center every 79.91 years. The distance between the stars varies from 35.6 astronomical units to 11.2 astronomical units. The distances are roughly equivalent to those between the Sun and Pluto and between the Sun and Saturn. An astronomical unit, to restate that in plain terms, is the average distance between Earth and the Sun, about 150 million kilometers. So at their greatest separation, A and B are about as far apart as the Sun is from Pluto. At their closest, they are as close as the Sun is to Saturn. By the standards of binary star systems, they are not far apart at all. This orbital intimacy is one of the first things that makes planet formation around these stars complicated. When two massive bodies orbit each other at relatively short separations, the gravitational environment for any forming planet becomes chaotic. Gravitational tugs from one star can perturb the orbit of a planet around the other, potentially flinging it out of the system entirely, or compressing its orbit into something extremely elongated. For decades, some theorists argued that stable planetary orbits within the habitable zones of either A or B were essentially impossible, that the mutual gravitational interference would disrupt planet formation before worlds could ever take root. Other theorists disagreed. They argued that stable orbital zones did exist around each individual star, particularly in what are called S-type orbits. Orbits where a planet circles one star rather than both, staying close enough to its primary that the binary companion's gravity is a perturbation rather than a disruption. The debate between these camps was not merely academic. It determined whether there was any point in searching for planets in this system at all. And for much of the 20th century, that debate remained unresolved. Stellar evolution theory suggests both stars are slightly older than the Sun, with age estimates typically ranging from around 5 to 6 billion years, as derived by their mass and spectral characteristics, though some methods yield values as low as 4.85 billion years. Think about what that means. Our own solar system, which formed roughly 4.6 billion years ago, has had time to produce Earth, life, and an entire civilization. Alpha Centauri A and B have existed for perhaps 500 million years longer than our Sun. If planets formed around these stars, and if those planets sat in stable zones, they would have had time, enormous, almost incomprehensible time, to develop. Alpha Centauri A has 1.1 times the mass and 1.5 times the luminosity of the Sun, while Alpha Centauri B is smaller and cooler, at 0.9 solar masses and less than half the Sun's luminosity. Alpha Centauri A, the slightly more massive and brighter of the two, is in many ways the most sun-like star within a reasonable observational distance from Earth. It is not an exact twin, but it is the closest thing we have. The third member of the system is different in almost every respect. Proxima Centauri is a smaller and cooler red dwarf star, located approximately 0.21 light-years away from the Alpha Centauri binary. It is known for its intense magnetic activity, which produces frequent flares and coronal mass ejections. If Proxima Centauri is gravitationally bound to the Alpha Centauri system, it orbits the binary pair with a period between 100,000 and 500,000 years. Proxima is, in the most literal sense, the star closest to our Sun, slightly closer than Alpha Centauri A and B at 4.2 light-years rather than 4.37. It is also the most extensively studied of the three in recent years because it turned out to have planets. In 2016, astronomer Guillaume Anglada-Escudé of Queen Mary University of London led a team of 31 scientists in a meticulous campaign called the Pale Red Dot Project. During the first half of 2016, Proxima Centauri was regularly observed with the HARPS spectrograph on the ESO 3.6-meter telescope at La Silla in Chile, and simultaneously monitored by other telescopes around the world. The campaign aimed to detect the tiny back-and-forth wobble of the star that would be caused by the gravitational pull of a possible orbiting planet. On August 24, 2016, the team led by Anglada-Escudé confirmed and announced the discovery of Proxima Centauri b, an Earth-mass planet in the habitable zone of Proxima Centauri. The planet, Proxima b, quickly became one of the most discussed worlds in the history of exoplanet science. It was Earth-sized. It was in the habitable zone. It was, in principle, reachable in a human lifetime if you had access to a spacecraft traveling at a significant fraction of the speed of light. The planet orbits within the habitable zone of its parent star, but it is not known whether it has an atmosphere which would impact the habitability probabilities. Proxima Centauri is a flare star with intense emission of electromagnetic radiation that could strip an atmosphere off the planet. The discovery was real. The excitement was real. But the complications were real too. In 2022, another planet named Proxima Centauri d, which orbits even closer to the star, was confirmed. So the smallest and most volatile member of the Alpha Centauri system turned out to be the one harboring confirmed worlds. And while the existence of Proxima's planets was electrifying, it also sharpened the question that had never really gone away. What about the two bigger, calmer, more sun-like stars at the heart of the system? What about A and B? The hunt for planets around those two stars has a long and somewhat painful history. For most of the early 21st century, astronomers tried to detect planets around Alpha Centauri A and B using the radial velocity method, the same technique Anglada-Escudé used to find Proxima b. The method works like this. When a planet orbits a star, its gravitational pull causes the star to wobble ever so slightly, moving minutely toward and away from Earth. A sufficiently sensitive spectrograph can detect this wobble by watching the star's light shift very slightly toward the red end of the spectrum as the star moves away and toward the blue end as it approaches. The shift is tiny. We are talking about velocities of meters per second, sometimes less. But with enough patience and precision, it can be measured. In October 2012, a team led by Xavier Dumusc of the Observatory of Geneva published a paper in Nature announcing the detection of a planet around Alpha Centauri b. The authors used radial velocity measurements to find a planet of approximately 1.13 Earth masses with a 3.236-day orbital period around Alpha Centauri b. The announcement was extraordinary. An Earth-mass planet in the nearest star system. The kind of discovery that rewrites textbooks, the kind that makes careers. The team had made observations extending over more than 4 years using the HARPS instrument and revealed what they described as a tiny but real signal from a planet orbiting Alpha Centauri b every 3.2 days. The celebration was short-lived. In October 2015, 3 years after the announcement of the initial finding, researchers from the University of Oxford published a paper entitled Ghost in the Time series, demonstrating flaws in the original analysis. The signal, it turned out, was likely an artifact of the statistical methods used to extract it from the data. A ghost produced by the analysis itself, not a real planet. This led Xavier Dumasque, the lead author of the original paper, to concede. We are not 100% sure, but probably the planet is not there. Consider what that moment meant for the field. Years of work, a paper in Nature, global headlines, and then, not a planet, just a pattern in the noise. It is worth sitting with that for a moment, not as a failure, but as a demonstration of how difficult this particular problem is. The Alpha Centauri system is extraordinarily hard to study, not because it is far away, but precisely because it is so close. Bright stars moving across the sky with measurable proper motion, orbiting each other every 80 years, producing subtle gravitational signals that contaminate radial velocity data in ways that can mimic planetary signals. The closeness that makes the system desirable also makes it one of the most technically demanding targets in all of exoplanet science. The ghost of Alpha Centauri b, as the non-planet came to be informally known, haunted the field for years. It was a reminder that wanting to find something and having instruments sensitive enough to almost but not quite find it is a dangerous combination. Science thrives on rigor precisely because the human mind is extraordinarily good at perceiving patterns, even patterns that are not there. So the stage was set, a system tantalizingly close. 2 sun-like stars old enough to have hosted ancient planetary systems, a history of false detections and retracted claims, confirmed planets around the violent red dwarf at the system's edge, and an absence, conspicuous, frustrating, unresolved, around the stars most like our own sun. Into this absence, in the summer of 2024, came the James Webb Space Telescope with its mid-infrared eye, a custom observing sequence designed by an entire operations team, and an approach to the problem that was fundamentally different from everything that had come before. The story of how Webb finally solved the problem of Alpha Centauri's glare is, in many ways, the story of how science advances, not in sudden leaps, but in a slow accumulation of better tools, sharper techniques, and the willingness to design something that has never been designed before. The core problem has always been the same. You cannot simply point a telescope at Alpha Centauri A and look for a planet. The star is too bright. In the infrared wavelengths where a planet would most readily reveal itself through its own heat, its own thermal glow, Alpha Centauri A is still thousands of times more luminous than any planet that could orbit it. And Alpha Centauri b, swinging around its binary companion in an 80-year waltz, hovers in the background of the image, spilling its own light across the detector in patterns that can mimic or mask planetary signals. Alpha Centauri A is the brightest of the 3 in the system, but its stellar companion Alpha Centauri b is still quite bright and quite close, crowding into telescope's fields of view. Although Webb is equipped with a coronagraph, a masking tool to block out the glare from one star, it cannot do much to curtail this second planet-obscuring source of light. The coronagraph deserves a proper explanation because it is the instrument at the heart of this story, and its simplicity belies its extraordinary precision. The concept was invented in 1930 by French astronomer Bernard Liot at the Meudon Observatory, who devised a way to block the overwhelming glare of the sun during solar observations by placing a small disk in the telescope's optical path, an artificial eclipse engineered at the focal plane. The same idea, refined over 9 decades of telescope design, now sits aboard the James Webb Space Telescope in a form that would have been incomprehensible to Liot. Webb's miricoronagraphy enables the direct detection and photometric characterization of exoplanets and disks in the mid-infrared, a wavelength regime previously inaccessible at high contrast and spatial resolution. The coronagraphs use advanced optical masks and precise calibration to capture high-contrast mid-infrared images of exoplanets and circumstellar disks. To state what that means in practical terms, the telescope reaches wavelengths of light, longer, warmer infrared wavelengths that had never been achievable from space with this level of clarity and contrast. MIRI implements 4 dedicated coronagraphs within its imager, 3 4-quadrant phase masks at 10.65, 11.30, and 15.50 micrometers, and a classical Lyot spot at 23 micrometers. The 4-quadrant phase masks enforce a phase shift in opposite quadrants of the focal plane, achieving on-axis suppression idealized to total cancellation for monochromatic light, delivering inner working angles of roughly 1 wavelength divided by the diameter of the telescope. What that technical language means, translated into physical experience, is this. Imagine holding a candle in front of your eye and trying to detect a firefly hovering 6 feet away from the flame. The candle swamps everything. Now imagine a precisely engineered mask that can block the candle's light so completely, without disturbing the space around it, that the firefly's faint glow becomes visible against the dark. That is, roughly, what MIRI's coronagraph does for a planet around Alpha Centauri A. The star is the candle. The planet, if it exists, is the firefly, and the 4-quadrant phase mask is the most refined blocking instrument ever sent to space. But even with this tool, the problem is not solved. It is only reduced, because the moment you block Alpha Centauri A's light, the residual glow of Alpha Centauri B, slightly displaced in the image but still substantial, bleeds across the detector. While extra brightness from the nearby companion star Alpha Centauri B complicated the analysis, the team was able to subtract out the light from both stars to reveal an object over 10,000 times fainter than Alpha Centauri A, separated from the star by about 2 times the distance between the Sun and Earth. That subtraction, that painstaking algorithmic removal of B's light from the image, leaving behind only the residual faint sources, is not a simple step. It required building reference images of both stars from other observations, then applying those reference images to the Alpha Centauri data as templates, peeling away the stellar glare layer by layer until what remained was, potentially, something else. Something that moved with the stars rather than staying fixed against the background sky. Something that was neither a galaxy nor an asteroid. Something that, in August 2024, appeared at a separation of approximately 2 astronomical units from Alpha Centauri A, 2 times the Earth-Sun distance, as a faint but consistent point source in the mid-infrared. These are incredibly challenging observations to make, even with the world's most powerful space telescope, because these stars are so bright, close, and move across the sky quickly, said co-first author Beichman. The challenge deserves emphasis. Alpha Centauri moves across the celestial sphere measurably from year to year, what astronomers call proper motion, because it is so close. It is not a fixed point in the night sky the way distant stars appear to be. It slides. And an instrument that takes long exposures of a drifting star needs to track that motion with extraordinary precision, or the image smears and everything is lost. The operations team had to come up with a custom observing sequence just for this target, and their extra effort paid off spectacularly, according to Bachman. That phrase, a custom observing sequence, understates what it means. It means that no existing mode of operation for the Webb Telescope was adequate for this target. The scientists and engineers working on this project had to invent, from scratch, a procedure for pointing, tracking, masking, subtracting, and ultimately extracting signal from a system that breaks every standard assumption built into telescope operations software. This is not unusual in frontier science, but it is rarely acknowledged for what it is: a small act of creation performed under pressure in service of a question that humans have been asking for as long as they have known that other stars exist. Take stock of where we are in the story so far. We have a triple star system 4.37 light-years from Earth. We have two sun-like stars, A and B, that have been circling each other for roughly 5 billion years, long enough for complex planetary systems to have formed and evolved. We have a history of failed detections around A and B, a ghost planet announced in 2012 and quietly retracted by 2015. We have a small confirmed planetary system around Proxima, the violent red dwarf at the system's outer edge, anchored by a discovery made in 2016 by astronomer Guillem Anglada Escudé. And we have a new instrument, the most powerful space telescope ever built, redesigned specifically to look at this one target, finally producing an image, finally producing a point source. But there is something that preceded even Webb's 2024 observation, a tantalizing earlier data point that had never quite solidified into certainty, and whose significance only became fully apparent when Webb's own results were in hand. And to understand it, you need to travel back to 2019, to a hilltop in the Atacama Desert of northern Chile, where a different instrument was pointing at the same two stars. The European Southern Observatory's Very Large Telescope stands at the summit of Cerro Paranal, an isolated mountain rising about 2,635 meters above the Atacama. The air at that altitude is dry enough, stable enough, and dark enough that ground-based telescopes there can achieve resolutions approaching those of space-based instruments on clear nights. In 2019, a team of astronomers used the NEAR instrument, New Earths in the Alpha Centauri region, a modified version of the VISIR mid-infrared camera, to conduct the most sensitive ground-based search ever attempted for planets around Alpha Centauri A and B. The initial detection of a planet candidate, labeled C1, was made by Wagner and his team in 2019, using the Very Large Telescope operated by the European Southern Observatory in Chile. The candidate appeared in the mid-infrared data. It was located at approximately 1.1 astronomical units from Alpha Centauri A, closer to the star than Earth is to the Sun, and technically within the system's habitable zone. But the signal was inconclusive. It was weak. It sat near the threshold of the instrument's sensitivity. It could not be ruled out as a background contaminant, a distant galaxy, an asteroid, an artifact of the atmosphere. The researchers also re-examined this puzzling 2019 observation of Alpha Centauri A from a ground-based telescope that, while constituting the first hint of a directly imaged planet there, never quite solidified into a confirmed world. This is science operating at its frontier, a signal that is just barely there, too faint to trust, too consistent to dismiss. The 2019 result, published in 2021 in Nature Communications, went into the scientific literature as a candidate, labeled C1, and waited. Then came Webb, and something appeared again. But not at 1.1 astronomical units, not at the position of C1. Something at approximately 2 astronomical units from Alpha Centauri A. A different location, a different angular separation, a different brightness. In 2024, the James Webb Space Telescope's mid-infrared instrument, which uses a coronagraphic mask to block the bright glare from Alpha Centauri A, revealed a potential planet, labeled S1, on the other side of the star. Now the puzzle deepened. The researchers had 2 observations, C1 from 2019, S1 from 2024, at different positions and different angular separations. Were they the same object, seen at different points in its orbit? Were they 2 different planets? Or were one or both of them not planets at all? There were now 2 telescopic observations of candidate planets, a smaller one observed by VLT at 1.1 astronomical units and a larger one by Webb at 2 astronomical units. Why did the VLT not see the larger Webb candidate? And why did Webb miss the VLT candidate across all 3 of its observations? These are the questions that the team led by Charles Beichmann of NASA's Exoplanet Science Institute and JPL, and PhD student Aniket Sanghi of the California Institute of Technology set out to answer through the one tool available when direct observations are incomplete: computational modeling. Millions of simulated orbits, millions of paths a planet might take around Alpha Centauri A, shaped by the gravitational field of A itself, perturbed by the presence of B at varying distances, constrained to remain gravitationally stable across the billions of years the system has existed. To investigate this mystery, the team used computer models to simulate millions of potential orbits, incorporating the knowledge gained when they saw the planet and when they did not. Sanghi is a co-first author on the 2 papers covering the team's research. The simulations incorporated not just the Webb observations and the VLT data from 2019, but also the orbital mechanics of the binary itself. The fact that Alpha Centauri B swings close to Alpha Centauri A every 80 years, and that only certain orbits around A remain stable in the presence of that recurring gravitational intrusion. In these simulations, the team took into account both the 2019 sighting of a potential exoplanet candidate by the European Southern Observatory's Very Large Telescope, the new data from Webb, and considered orbits that would be gravitationally stable in the presence of Alpha Centauri B, meaning the planet wouldn't get flung out of the system. What emerged from this computational search was a coherent picture. A single world, tentatively identified as the most likely interpretation of both C1 and S1 combined, following an elliptical orbit around Alpha Centauri A, sweeping between approximately 1 and 2 astronomical units from the star over a period of roughly 1.5 to 2.5 Earth years. An orbit that takes it into the habitable zone, and perhaps beyond it, and back again. By piecing together the 4 observations, a single, plausible world could emerge. A cool Saturn-mass planet looping around the star every roughly 2 to 3 Earth years on an elongated elliptical orbit. The 2019 and 2024 observations caught the planet next to the star, the hypothesis goes, while the 2025 ones were unlucky enough to miss the planet while it was out of sight, in front of or behind the star. This is where the story of the disappearing planet comes in. And it is one of the most remarkable aspects of the entire investigation. Because when Webb returned to Alpha Centauri A in February 2025, and again in April 2025, using what is called director's discretionary time, time reserved for high-priority targets of immediate scientific relevance, the additional observations did not reveal any objects like the one identified in August 2024. The planet had vanished, or more precisely, it had vanished from the field of view, gone behind its star, or swung so close to Alpha Centauri A that Webb's coronagraph could no longer distinguish it from the stellar halo. The researchers found that 52% of the stable orbits that fit the combined S1 and C1 astrometry are also consistent with non-detections in both February and April 2025. There is, thus, an a priori significant chance that, if real, the planet candidate could have been missed in both follow-up observation epochs. The team found that in half of the possible orbits simulated, the planet moved too close to the star and wouldn't have been visible to Webb in both February and April 2025. This is the key result, and it is worth dwelling on. The non-detections in 2025 are not evidence against the planet's existence. In half of the simulated orbital scenarios, consistent with what was seen in 2019 and 2024, the planet would be expected to be invisible in exactly the observation windows when Webb looked and found nothing. The absence, in other words, is predicted by the hypothesis. It is what you would expect to see if a planet on an elliptical orbit periodically dips behind or beside its star. This kind of reasoning, where a non-detection is used as an affirmative constraint rather than a refutation, is subtle but powerful. It represents a mature approach to incomplete data. Instead of declaring failure, the team asked what orbital geometries are consistent with all 4 data points simultaneously, including the 2 that saw something and the 2 that saw nothing. The answer was a coherent, physically plausible planetary orbit. Based on the brightness of the planet in the mid-infrared observations and the orbit simulations, researchers say it could be a gas giant, approximately the mass of Saturn orbiting Alpha Centauri A, in an elliptical path, varying between 1 to 2 times the distance between the Sun and Earth. The mass estimate comes from the brightness. A planet glows in the infrared because it retains heat from its formation, a warmth that dissipates very slowly over billions of years, radiating into space as a faint thermal signature. The brightness of S1 in Webb's mid-infrared image translates, through models of planetary cooling and atmospheric physics, into a rough mass estimate. Saturn-like, roughly 95 times the mass of Earth, give or take. Not a rocky terrestrial world, a gas giant, a swirling sphere of hydrogen, helium, and heavier compounds, with no solid surface to stand on, no liquid water pool to sustain biology as we understand it. If confirmed, the potential planet seen in the Webb image of Alpha Centauri A would mark a new milestone for exoplanet imaging efforts. Of all the directly imaged planets, this would be the closest to its star seen so far. It is also the most similar in temperature and age to the giant planets in our own solar system, and nearest to our home, Earth. Its very existence in a system of 2 closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. That last sentence is the one that resonates most deeply, and it is worth unpacking before moving on. The very existence of a gas giant in a stable orbit around one star of a close binary, where the other star swings within the equivalent of Saturn's distance from the Sun every 80 years, challenges some of the most fundamental models of planetary formation and dynamical evolution that astronomers have built over the past 3 decades. Picture how a planet forms. You start with a disk of gas and dust swirling around a newborn star, a protoplanetary disk, the remnant material from the same cloud that collapsed to create the star itself. Over millions of years, dust grains collide and stick together, forming pebbles, then boulders, then kilometer-sized bodies called planetesimals. Planetesimals crash into each other, building up rocky cores. If a rocky core grows massive enough, somewhere around 10 Earth masses, models suggest, it can begin to gravitationally attract gas from the surrounding disk, growing rapidly into a gas giant. This process, called core accretion, is believed to be how Jupiter and Saturn formed in our own solar system. But this process takes time. It takes millions of years for the cores to grow, and then more years for the gas to accumulate. And in the Alpha Centauri system, the timer runs differently. Every 80 years, Alpha Centauri b comes swinging relatively close, producing gravitational tides that could stir the protoplanetary disk around Alpha Centauri a, preventing dust from settling, disrupting the gentle accumulation of larger bodies, scattering planetesimals away before they can grow. Whether a planet can actually form under those conditions, and whether, having formed, it can maintain a stable orbit for 5 billion years, is a question that this candidate, if confirmed, would answer with a definitive and somewhat startling yes. The textbook answer, the one that dominated planetary science for decades, is that close binaries like Alpha Centauri AB are hostile to planet formation around the individual stars. That picture has been repeatedly challenged by observations, and this candidate challenges it most dramatically of all. The Saturn-mass planet around Alpha Centauri A, if it is real, sits in a habitable zone. That phrase deserves careful attention because it is one of the most commonly invoked and most commonly misunderstood concepts in all of planetary science. The habitable zone is not, in itself, a guarantee of anything. It is a zone of possibility defined by a specific physical criterion: the range of orbital distances from a star where a planet with a suitable atmosphere could maintain liquid water on its surface. Not too hot, not too cold. The distance window depends on the star's luminosity. For a star like Alpha Centauri A, somewhat brighter than the Sun, the habitable zone is pushed slightly outward compared to our own solar system's equivalent. And the candidate planet, S1, follows an elliptical path that carries it through roughly that range. But here's what almost nobody tells you about the habitable zone when the planet in question is a gas giant. The gas giant itself is not habitable. Not by any biology we can conceive of. It has no solid surface. Its atmosphere, if it resembles Saturn's, is a layered structure of hydrogen, helium, ammonia ice crystals, and complex organic haze. A place of crushing pressures, extreme cold at the cloud tops, and extreme heat and pressure at depth. The candidate planet, based on its brightness in the mid-infrared observations, has a modeled temperature estimated at roughly 200 to 350 Kelvin, which translates to somewhere between -70 and +80 degrees Celsius at the level where models place its photosphere, though this estimate carries significant uncertainty. That range spans conditions that water can exist in on a planetary surface, but there is no surface. There is only more gas, deepening and compressing as you descend. So why does its position in the habitable zone matter at all? It matters for 2 reasons that operate at very different scales. One intimate and specific, one grand and philosophical. The intimate reason is moons. Gas giants are almost universally orbited by systems of moons, sometimes dozens of them. In our own solar system, Saturn has at least 274 confirmed moons, ranging from tiny irregular captured objects to Titan, a moon larger than the planet Mercury, wrapped in an atmosphere of nitrogen and methane, with lakes of liquid hydrocarbons pooling on its surface. Jupiter has Ganymede, the largest moon in the solar system, and Europa, whose icy surface conceals a subsurface ocean of liquid water that may be one of the most promising environments for life in the entire solar system. If the Alpha Centauri A candidate is real, and if it hosts moons of substantial size, and there is no physical reason it could not, then those moons sit in the habitable zone of a sun-like star, bathed in approximately the right amount of stellar radiation, warmed additionally by the tidal flexing that comes from orbiting a massive planet. The planet would not support life as we know it, but as one researcher put it, while the candidate planet is a gas giant, scientists say it would not support life. The phrase, "as we know it," hides an enormous amount of possibility in the space of what we do not yet know. There is a caution here, though, and it is important. Some researchers have noted that the eccentricity of the candidate's orbit, the elongation of its elliptical path, may itself be a problem for moons. A planet on a highly elliptical orbit experiences significant variations in stellar irradiation over the course of its year. What is warm and temperate at the far end of the orbit may become hot and hostile at the close approach. Moons, which inherit much of their parent planet's orbital dynamics, would be subjected to the same fluctuations. The conditions at any given moon's surface would oscillate seasonally in ways very different from Earth's relatively mild axial tilt variations. Whether biology could adapt to those oscillations, or whether the oscillations themselves might drive interesting chemistry, is something we cannot currently say. The philosophical reason the habitable zone matters is more expansive. It is about what the existence of this planet tells us about planetary systems in general, and about the likelihood that complex worlds exist in the most accessible corners of our galaxy. For decades, the implicit assumption in the search for habitable planets was that you needed a solar system like ours, a single star, a relatively stable architecture, a circular orbit in a narrow Goldilocks band. That assumption has been eroded by 20 years of exoplanet science, which has revealed an almost incomprehensible diversity of planetary arrangements. Hot Jupiters orbiting in days, super-Earths with no solar system analog, multi-planet systems packed so tightly that gravity barely holds them stable, binary stars with planets orbiting both stars at once. The universe, it turns out, does not share our preference for familiar arrangements. It experiments. It builds worlds in places we assumed were too hostile, too crowded, too gravitationally complex to sustain them. The Alpha Centauri candidate is one more data point in that long argument. Its very existence in a system of two closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. And challenges to understanding are not setbacks. They are invitations. They are the universe informing us politely but firmly that our models are incomplete. Now consider the question of what kind of planet this actually is. The mass estimate, roughly Saturn's mass, perhaps up to 200 Earth masses, comes from the photometry, the brightness of the object in Webb's mid-infrared image. But photometry alone cannot distinguish cleanly between a planet and other possibilities. Several rounds of meticulously planned observations by Webb, careful analysis by the research team, and extensive computer modeling helped determine that the source seen in Webb's image is likely to be a planet, and not a background object like a galaxy, a foreground object such as a passing asteroid, or other detector or image artifact. That process of elimination, ruling out everything that is not a planet before, concluding that a planet is what remains, is the heart of astronomical detection at this level of sensitivity. The planet is a bit brighter than expected for its type, so zodiacal dust could be contributing. Zodiacal dust, the fine particulate matter from comets and asteroid collisions that spreads across a planetary system in a diffuse cloud, can glow in the infrared and contaminate measurements. If the Alpha Centauri system has an extensive exozodiacal dust cloud around its inner region, some of the brightness attributed to the candidate planet might actually be dust. The teams accounted for this in their analysis, placing upper limits on the zodiacal dust contribution and finding that even in scenarios with a significant dust component, a planetary source is still required to explain the observed signal. But the uncertainty remains, and it is one of the reasons the papers describe this as a candidate rather than a confirmed detection. The planet could also be rotating rapidly, and if viewed from the pole, could show more surface area, which would increase its apparent brightness. Or it could have rings, like Saturn. The possibility of a ring system is not frivolous. Saturn's rings are one of the most visually spectacular structures in our solar system, and they contribute meaningfully to Saturn's brightness at certain wavelengths. A young, massive ring system around a gas giant in the Alpha Centauri system could plausibly make the planet appear brighter than models would otherwise predict, without requiring any exotic physics. More than one interpretation fits the data. This is worth sitting with. The candidate, designated S1, represents a convergence of multiple lines of evidence: the 2019 VLT detection, the 2024 Webb detection, the computational modeling of millions of orbits, into a single self-consistent picture. But self-consistency is not confirmation. Science requires the convergence to hold up under fresh observation at different times with different instruments, ideally by independent teams working independently. That confirmation has not yet arrived. It may come soon. It may require years. It may come in the form of a redirection, a new observation that rules out the planet and points toward a different explanation. That is the nature of frontier science. It does not progress in straight lines. What the researchers could say with confidence by the time the two papers were accepted for publication in the Astrophysical Journal Letters in 2025 is this: there is a point source in the Alpha Centauri A system that is inconsistent with known sources of instrumental noise, stellar glare artifacts, background galaxies, and solar system foreground objects. That point source appeared at a separation from Alpha Centauri A, consistent with orbital motion. Its brightness is consistent with a Saturn-mass gas giant at roughly 200 to 350 Kelvin. Its disappearance in 2025 is consistent with roughly half the orbital scenarios that fit the combined 2019 and 2024 detections. The simplest explanation, though not the only possible one, is a planet. Step back for a moment. See the full picture of what this moment represents in the history of the search for nearby worlds. In 1995, Swiss astronomers Michel Maillot and Didier Queloz detected the first planet around a sun-like star, 51 Pegasi b, by measuring the wobble it induced in its parent star's radial velocity. That discovery, made at the Haute-Provence Observatory in southern France, launched a revolution. Within 2 decades, astronomers had detected thousands of exoplanets. The Kepler Space Telescope, launched in 2009, found planets by the thousands using the transit method, watching stars dim ever so slightly as planets passed in front of them. But transit photometry has an intrinsic geometric bias. It it can only detect planets that happen to pass between their star and Earth from our viewing angle. It is extraordinarily powerful for distant, compact systems, but nearly useless for the kind of wide solar system-like orbits where planets of the most interest for habitability tend to reside. Direct imaging is different. Direct imaging captures the light, or in this case, the thermal emission, of the planet itself. It is the most direct measurement possible. You are seeing the object, not its gravitational shadow or its obstruction of starlight. But it requires the ability to separate a point source that may be 10,000 times fainter than its host star from the overwhelming glare of that star, at angular separations that, even for Alpha Centauri, correspond to fractions of an arc-second. That is why direct imaging of cold, distant planets has historically been limited to very young systems where planets are still hot from formation, or to very wide separation objects far from their stars. The S1 candidate, if confirmed, would be the nearest planet directly imaged in orbit around a solar-type star, the coldest, the oldest, and the one orbiting in the shortest period. It would be, in the words of the research team, the nearest, coldest, oldest, shortest period, and lowest mass planet imaged in orbit around a solar-type star to date. That collection of superlatives matters. It is not merely a list of records. It is a description of a genuinely new kind of target, a planet close enough and cold enough that follow-up observations would tell us things about planetary atmospheres, planetary formation in binary systems, and planetary evolution over billions of years that no other known directly imaged planet could provide. This would become a touchstone object for exoplanet science, with multiple opportunities for detailed characterization by Webb and other observatories. What could future observations reveal if the candidate holds up? The most immediate prize would be spectroscopy. Once you can reliably detect the planet's thermal emission, you can try to spread that light into its component wavelengths, a spectrum, and read the chemical fingerprints of the planet's atmosphere from the absorption and emission features in that spectrum. Different molecules absorb infrared light at characteristic wavelengths. Ammonia has a strong absorption band at 10.65 micrometers, precisely the wavelength range where Webb's Miri coronagraph operates. Methane, carbon dioxide, water vapor. If a Saturn-like gas giant at Alpha Centauri A has any of these molecules in detectable abundances, a sufficiently long spectroscopic observation with Webb could, in principle, reveal them. This kind of atmospheric characterization, reading the composition of a planet's air from 4 light-years away, would be one of the most extraordinary scientific achievements in history. And it would not require traveling to Alpha Centauri or even building a new telescope. It would require confirming that S1 is real, finding it again in a future observation window, and then pointing Webb's spectrograph at it for a long time. Some researchers think the best window for another attempted detection would come in late 2025 or early 2026, when the orbital simulations predict the planet should be near its greatest angular separation from the star and therefore most detectable against the reduced stellar halo. The observations and orbital simulations provide a prediction for where the planet will be in the future. This is the cadence of science at the frontier. Predict, observe, refine, or revise. The prediction is in place. The observation is pending. The outcome is not yet known. And here is where a different kind of complexity enters the story. One that sits not in the data, but in the history of this particular system and this particular quest. A complexity that makes the current moment both exciting and cautious at the same time. Everyone who has searched for planets around Alpha Centauri A and B has wanted to find them. The proximity of the system makes it an almost irresistible target. The human longing for a world next door, a planet around the nearest sun-like star, close enough that future technology might one day reach it, infuses every observation with a weight that pure data does not carry. That longing is not a flaw. It is part of what makes science a human enterprise. But it is also a source of potential error, and the history of this system is littered with the ghosts of detections that turned out, on closer inspection, to be something else. Alpha Centauri. B, the ghost of 2012, is the most prominent example, but it is not the only one. Several other candidate signals have appeared in radial velocity datasets over the years, only to dissolve when the data were reanalyzed with improved statistical methods. Some researchers think there are orbital signals in the HARPS data that are still unexplained. Others think the confusion in the data runs deep enough that the question of planets around A and B cannot be cleanly answered through radial velocity at all, and that direct imaging, precisely what Webb is now attempting, is the only path to reliable detection. Some researchers argue that the S1 candidate represents compelling evidence that should drive follow-up observations as a priority. Others maintain that the combination of one clear detection, one ambiguous earlier detection, and two non-detections does not constitute strong evidence, and may still, upon further investigation, point toward an astrophysical background source or an instrumental artifact. In presenting contested claims, the scientific community must hold both perspectives seriously. The evidence is not nothing. But it is also not yet enough to declare a discovery. The team themselves acknowledge this with unusual transparency. With only a single Webb/MIRI sighting and non-detections at two other epochs, it is challenging to uniquely constrain the orbit of S1. There is a significant chance that, if real, the planet candidate could have been missed in both follow-up observation epochs. The language is carefully calibrated, candid about uncertainty in a way that is rare in science communication, where the pressure to claim discoveries can distort measured language into premature announcement. Picture yourself standing in the Atacama Desert on a clear night at the summit of Cerro Paranal, looking south toward the constellation Centaurus. Alpha Centauri burns above the horizon, brilliant, unwavering, steady as a heartbeat. You know, standing there, that this system has been scrutinized by every major telescope on Earth and in space for the better part of a century. You know that it has resisted clarity, that it has offered hints and withdrawn them, that it has demanded more and more sophisticated instruments with every passing decade. And you know that right now, at this moment, there is a point in the infrared image of one of those two bright stars, a point source 10,000 times fainter than the star itself, whose interpretation of the field has not yet been resolved. That uncertainty is not a failure. It is a location. It marks where the frontier currently runs. And the frontier in science is not a wall. It is a threshold. Anaphora helps to describe what the last century of Alpha Centauri observation has produced. We built instruments precise enough to detect the wobble of a star perturbed by a planet. We built models sophisticated enough to simulate the gravitational interactions of a binary star system over billions of years. We built telescopes cold enough and sensitive enough to detect the thermal glow of a gas giant at 4 light-years. And we are still not certain. Still not certain. Still asking, with every new observation, whether what we are seeing is real. That persistence, in the face of such compounding difficulty, is itself a kind of wonder. Not the wonder of having arrived somewhere, but the wonder of the approach, of instruments and minds working together at the very edge of what physics currently allows. There is one more layer of complexity to the Alpha Centauri system that has not yet been fully addressed, and it concerns the third star, Proxima, and what its confirmed planetary system means for our understanding of the binary's own planet-forming history. These are not unrelated questions. They are bound together by gravity and time. Proxima Centauri, to recall, is a red dwarf. The smallest and faintest of the three stars, it lies about 0.24 light-years from Alpha Centauri A and B, and is almost certainly gravitationally bound to them, though its orbital period around the binary center is estimated at between 100,000 and 500,000 years. Proxima is also a flare star, prone to sudden, intense bursts of ultraviolet and X-ray radiation that can briefly increase its brightness and hammer any nearby planets with particle radiation. In 2016, Guillem Anglada Escudé confirmed Proxima b, an Earth-mass planet in Proxima's habitable zone, orbiting every 11 Earth days at a distance of roughly 0.05 astronomical units from its star. In 2022, Proxima d, an even smaller planet in a tighter orbit, was confirmed. A third candidate, Proxima c, remains disputed. The planet orbits within the habitable zone of its parent star, but it is not known whether it has an atmosphere. Proxima Centauri is a flare star with intense emission of electromagnetic radiation that could strip an atmosphere off the planet. This is the central tension of Proxima b. Its location is compelling, inside the habitable zone, with enough stellar energy to maintain liquid water if an atmosphere exists. Its environment is hostile. The same flares that make the star interesting are violent enough, with sufficient frequency and energy that they may have scoured away any atmosphere Proxima b once possessed. The comparison between Proxima's confirmed planets and the candidate around Alpha Centauri A is structurally revealing. One system, Proxima's, is confirmed but possibly uninhabitable, its planets battered by the radiation of a violent host. The other, Alpha Centauri A's, is unconfirmed but, if real, would reside around a gentler, more sun-like host with a luminosity profile similar enough to our own star that concepts like habitable zones map onto it more cleanly. This contrast is not merely scientific. It reflects a broader truth about the nature of discovery. The places most likely to host complex chemistry or biology are not always the places we find first. The places we find first are the places easiest to detect, which means, in exoplanet science, small tight orbits, bright host stars, and favorable viewing geometries. The places hardest to detect are often, by virtue of their dynamical gentleness, the places most conducive to the long timescale processes that life requires. Alpha Centauri A, sitting quietly behind its wall of glare, may have been hiding the most important real estate in the neighborhood all along. The planet, S1, the candidate, the vanishing world, would, if confirmed, represent something more than a new data point. It would represent the fulfillment of a century of frustrated searching. It would mean that the star most like our own sun within a meaningful range has at least one world. It would mean that the nearest stellar system is not barren. It would mean that the address at the end of our cosmic street, 4.37 light-years away, is inhabited, not by life necessarily, but by matter, organized into a sphere, held in orbit by gravity, bathed in starlight. That is, in itself, extraordinary. The question of what it means to find a world, or the strong suggestion of a world, around the star most like our own sun within striking distance, deserves more than a single angle. It deserves to be examined from several directions simultaneously, the way a geologist examines a rock formation. turning it over, looking at the grain structure, testing what it tells you about the forces that shaped it. Because the Alpha Centauri candidate does not exist in isolation. It exists within a conversation, a decades-long instrument-by-instrument, paper-by-paper conversation about how planets form, how they survive, and what the architecture of planetary systems tells us about the universe's deep preferences. Start with formation. The standard model of planet formation, core accretion, has been extraordinarily successful at explaining the broad outlines of our own solar system. Rocky planets form close to their star, where temperatures were high enough in the protoplanetary disk that only refractory materials, silicates, metals, minerals, could condense into solid grains. Gas giants form farther out, beyond the snowline where water and other volatiles freeze into ice, giving growing planetary cores more raw material to work with. In our solar system, the snowline sits at roughly 2.7 astronomical units. Jupiter formed somewhere near 5 astronomical units, Saturn at 9. The architecture has a logic to it, shaped by temperature gradients and the timescale of disk evolution. Now apply that framework to Alpha Centauri A. The candidate planet, S1, is estimated to orbit at between 1 and 2 astronomical units from its star, inside or at the inner edge of the zone where snowlines would have existed during the system's formation, roughly 5 billion years ago. At those distances, during the hot early period of the protoplanetary disk, forming a massive gas giant through classical core accretion would have been slow enough that some models suggest the disk dissipates before the core grows large enough to accrete a substantial gas envelope. This is one of the reasons some theorists argued that gas giants should not exist in such tight orbits around their stars unless they migrated there from farther out. Migration. The word is one of the most consequential in modern planetary science, and it upended the clean picture that the solar system's architecture had suggested. In the 1990s, theorists began working out in detail how a forming planet, embedded in the gas and dust of a protoplanetary disk, inevitably exchanges angular momentum with the disk material around it. This exchange causes the planet to spiral inward or outward, depending on the specifics, in a process that can carry a gas giant from beyond the snowline to a position very close to its star, over timescales of millions of years. The first exoplanet detected around a sun-like star, 51 Pegasi b, discovered by Meyer and Queloz in 1995 at the Haute-Provence Observatory in southern France, was a gas giant in a 4-day orbit, impossibly close by solar system standards. Its existence made no sense under pre-migration thinking. With migration, it made perfect sense. It had formed far out and spiraled inward. Migration almost certainly reshaped our own solar system too. In a grand scenario developed over the early 2000s by researchers, including Alessandro Morbidelli of the Observatoire de la Côte d'Azur in Nice, France, Jupiter and Saturn underwent a period of dynamical instability in the early solar system that caused their orbits to shift substantially, scattering planetesimals throughout the system, possibly triggering the late heavy bombardment recorded in the cratered surfaces of the Moon and Mars. The solar system's current architecture is not its original one. It is the product of billions of years of gravitational sculpting, of near misses and close encounters, and cascading orbital adjustments. If the Alpha Centauri A candidate formed through core accretion beyond the binary's snowline, perhaps at 3 or 4 astronomical units, and then migrated inward to its current position, that would be entirely consistent with what we know about planetary evolution. But the binary companion adds a layer of complication. As Alpha Centauri b sweeps through its closest approach every 80 years, its gravitational influence truncates the protoplanetary disk around Alpha Centauri A at a certain radius. Some models place this truncation radius at roughly 2 to 3 astronomical units, depending on the disk's properties and the binary's orbital inclination. If the disk was truncated at 2 astronomical units, a gas giant forming beyond that radius would have had a limited reservoir of material to draw from, limiting either its final mass or the rate at which it could grow. The candidate's estimated mass, roughly Saturn's mass, approximately 95 Earth masses, is consistent with a formation history where core accretion proceeded normally, but gas accretion was cut short by disk dispersal, or where the planet formed in a truncated disk with a limited gas supply. It is also consistent with a planet that formed at a larger distance and migrated inward, shedding some of its original mass through interaction with the disk during migration, a process sometimes called Type II migration in the theoretical literature. Different processes, similar outcomes. The data cannot yet distinguish between them. Some researchers think a different formation pathway, gravitational instability, is more appropriate for systems like Alpha Centauri. In gravitational instability, a sufficiently massive and cool protoplanetary disk fragments directly into bound clumps, which collapse rapidly into gas giants without the slow core-building step. This process is faster, thousands of years rather than millions, and might be favored in binary systems where the gravitational perturbations from the companion star cause density waves in the disk that seed instabilities. Others think gravitational instability produces only very massive planets at wide separations, and that the Saturn-mass candidate at 1 to 2 astronomical units is better explained by core accretion. Some researchers argue one scenario, others argue the other. The truth, as is often the case in planetary formation science, may depend on initial conditions that were set 5 billion years ago and left no recoverable record. What both scenarios agree on is that if the planet exists, and is where the models say it is, its very survival across 5 billion years in a binary system represents a triumph of orbital mechanics over gravitational disruption. The planet has been doing a complex gravitational dance for 5 billion years, pulled by Alpha Centauri A, perturbed every 80 years by the approach of Alpha Centauri B, possibly nudged by any other planets in the system. And it has not been ejected. It has not crashed into its star. It has not drifted into an unstable resonance. It persists. That persistence is itself a physical statement about the range of conditions under which planets can survive. The orbital eccentricity of the candidate adds another dimension to this statement. The simulated orbits that fit the data suggest an eccentricity of roughly 0.4, meaning the planet's orbit is noticeably elongated, with its closest approach to Alpha Centauri A significantly smaller than its farthest point. An eccentricity of 0 would mean a perfectly circular orbit, like Earth's nearly circular path. An eccentricity of 0.4 means the difference between closest approach and farthest point is substantial. For comparison, Mercury, the most eccentric of the solar system's inner planets, has an eccentricity of 0.206. The candidate at Alpha Centauri A is more eccentric than Mercury. This eccentricity is almost certainly the fingerprint of Alpha Centauri B's gravitational influence. Binary companions are known to excite eccentricities in the orbits of planets around the primary star, through a mechanism called the Lidov-Kozai effect, and through secular gravitational perturbations that accumulate over long orbital timescales. The eccentricity is not a flaw in the planet's orbit. It is a scar, or perhaps more accurately, a record, of billions of years of gravitational conversation between the planet and the binary companion. It tells a story. Reading that story properly will require far more data than currently exists, but the story's existence is itself significant. Pause here because something worth dwelling on has just emerged from this technical discussion. The orbital eccentricity of the candidate planet, if it exists, means that its distance from Alpha Centauri A changes substantially over the course of its year. At its farthest point from the star, the planet receives less stellar irradiation than Earth does from the Sun. At its closest approach, it receives considerably more. A planet, or a moon of a planet, at that orbital position would experience a seasonal variation in stellar irradiation far more extreme than anything in our solar system. It would move in and out of the habitable zone as it traverses its own orbit, spending part of each year in relative warmth and part in greater cold. Whether this cyclical variation in stellar heating is a barrier to life or merely a different kind of habitat is a question that the science of astrobiology has only recently begun to explore seriously. The dominant view for most of exoplanet science's short history has been that habitability requires stability. A nearly circular orbit, a mild and consistent stellar environment, the kind of predictability that allows oceans to remain liquid and climates to remain clement across geological timescales. But life on Earth does not require stability. It requires chemistry. And chemistry is sensitive to energy gradients as much as to steady energy inputs. Some astrobiologists argue that eccentric orbits, by producing strong seasonal forcing on a planetary surface, might actually drive chemical cycling that accelerates the emergence of biological complexity, though this remains speculative, with no consensus yet formed. The intellectual landscape here is genuinely open. It is not settled science with a clear answer that researchers are merely working to confirm. It is a frontier, and the frontier is wide. Now turn to the question of what the broader survey of nearby stars tells us about the plausibility of the Alpha Centauri candidate. The field of exoplanet science has not been idle while the search around Alpha Centauri A and B produced ambiguous results. Over the past 3 decades, astronomers have surveyed thousands of nearby stars for planetary companions, using the full toolkit of available methods: radial velocity, transit photometry, direct imaging, astrometry, and gravitational microlensing. The census that has emerged is one of the most important empirical results in the history of astronomy. Planets are common, extraordinarily common. The Kepler Space Telescope's statistical analyses, led by researchers including Natalie Batalha at NASA Ames Research Center in the early 2000s, established that virtually every Sun-like star has planets. The occurrence rate of Earth-sized planets in the habitable zones of Sun-like stars, the thing that exoplanet science has been working toward for 2 decades, is estimated to be somewhere between a few percent and a few tens of percent, depending on the survey and the methodology. Gas giants like the Alpha Centauri candidate are somewhat less common in close orbits around Sun-like stars. The occurrence rate for Saturn-mass planets at 1 to 2 astronomical units is estimated at roughly 10 to 15% in the current literature, though this number carries substantial uncertainty because the relevant parameter space is only partially covered by existing surveys. What that means, in concrete terms, is that a Saturn-mass gas giant at 1 to 2 astronomical units around a Sun-like star is unusual, but not extraordinary. It is the kind of planet that exists. It is the kind of planet that the theory of core accretion can produce, and that migration can take place where the data seem to indicate it is. There is nothing physically implausible about it. The question is not whether such a planet could exist at Alpha Centauri A. The question is whether the data are telling us this particular example does. Here's where the instrumentation story becomes inseparable from the scientific story. Every method of planet detection has blind spots, regions of parameter space where it is essentially insensitive. Radial velocity struggles to detect planets in wide orbits because the period of a planet at 1 to 2 astronomical units from its star is 1 to 3 years, and radial velocity surveys need multiple orbital periods to establish a detection with confidence. Alpha Centauri A and B have been monitored with radial velocity instruments for decades, and the sensitivity at the relevant orbital distances is estimated at roughly 50 Earth masses for the habitable zone, meaning that any planet less massive than about 50 Earths at those distances would be invisible to current radial velocity methods, drowned in the stellar noise produced by the binary's own orbital dynamics and by stellar activity. The candidate S1, at roughly 95 Earth masses, would in principle be detectable by radial velocity, but only barely, and only in data clean enough that the binary's influence can be subtracted reliably. That condition has not yet been met. Transit photometry cannot find this planet at all. The probability that a planet at 1 to 2 astronomical units from its star will happen to orbit in a plane that causes it to pass directly between its star and Earth is less than 1% for that orbital distance. The geometric lottery is heavily against it. Direct imaging in the mid-infrared with a space-based coronagraph specifically designed for this target. That is the only method currently able to reach this regime. And it found something. In August 2024, at the limit of what the most powerful telescope humanity has ever launched into space can do, it found something. Something that is real. Something 10,000 times fainter than its star, sitting 2 astronomical units away, glowing faintly in the infrared with the warmth of a world that has been cooling since before Earth's first continents formed. Something that appeared in August 2024 was gone in February and April 2025, and whose disappearance is predicted by half of all the orbital scenarios consistent with the combined dataset going back to 2019. That is not nothing. That is, in fact, the best evidence currently in existence for a planet around Alpha Centauri A. And given the history of this system, the decades of false starts, the ghost planet of 2012, the tantalizing but inconclusive VLT result of 2019, the fact that the best available evidence now consists of a multi-epoch, multi-instrument dataset with a self-consistent orbital solution represents genuine and significant progress. Progress that is not yet a conclusion, but that is clearly advancement. Take a moment to look back at the path we have traveled through this story so far. We began with a triple star system, A, B, and Proxima, at 4.37 light-years, the nearest stellar address to our own. We traced the history of the search for planets there, from decades of radial velocity monitoring through the retracted 2012 detection of a ghost planet, to the 2016 confirmation of Proxima b and the 2019 VLT hint of something near Alpha Centauri A. We examined how Webb's mid-infrared instrument, with its coronagraph and its custom observing sequence, finally produced a point source in August 2024. An object 10,000 times fainter than its star, at the right distance, with the right brightness, for a Saturn-mass gas giant in the habitable zone. We traced the simulations that showed the planet's 2025 disappearance is not a refutation, but a prediction, consistent with roughly half of all stable orbital solutions. And we have been examining what this candidate, if real, tells us about planetary formation in binary systems, about the survival of orbits under gravitational perturbation, and about the plausibility of worlds in the most intimate neighborhood of our own solar system. Now we move to a layer deeper, to the questions that the existence of this candidate opens up rather than closes down. Because the most significant implications of the Webb finding are not contained in its current data. They are contained in what the current data makes newly possible, newly urgent, and newly worth asking. One of the most important of those questions concerns the relationship between the confirmed planets around Proxima Centauri and the candidate around Alpha Centauri A, and what that relationship tells us about whether the entire Alpha Centauri system, all 3 stars, all their planets and candidates, formed from a common molecular cloud. Stars that form together from the same giant molecular cloud inherit similar chemical compositions, similar elemental ratios. If the Alpha Centauri system is a true coeval triple, if all 3 stars formed from the same collapsing cloud at roughly the same time, then the planets around each star should share a baseline chemical inventory. The silicate minerals in a rocky planet around Proxima should have been built from the same pool of raw materials as any rocky cores around A and B. The ratio of oxygen to carbon, of iron to silicon, of volatile elements to refractory ones, these would be set by the original cloud, not by anything that happened afterward. This matters enormously for the question of habitability, because planetary habitability is not just about distance from a star. It is about chemistry. Whether a planet can maintain plate tectonics, which recycles carbon dioxide back into the mantle and regulates the long-term temperature of the atmosphere, depends in part on the ratio of iron to silicate in the mantle. Whether a planet can maintain a magnetic field which protects its surface from stellar radiation depends on the size and composition of its iron core. Whether a planet can maintain oceans depends on how much water was delivered during formation, which depends on the volatile content of the building blocks available in that part of the protoplanetary disk. A confirmed planet around Alpha Centauri A, with detectable spectral features, would allow astronomers to measure the chemical composition of its atmosphere, the ratios of carbon to oxygen, the presence or absence of sulfur compounds, the abundance of nitrogen relative to hydrogen. Those measurements would illuminate not just the planet's own nature, but the chemical environment from which it formed. They would provide the first direct chemical window into the material that built worlds in the Alpha Centauri system. For a system that appears to have been producing planets around at least one of its stars, and possibly 2 or 3, that window would be extraordinarily valuable. This is where Webb's potential as a follow-up instrument becomes genuinely transformative. Among nearby stars, Alpha Centauri A offers a nearly 3-fold improvement in the angular scale of its habitable zone and a 7.5-fold boost in the absolute brightness of any planet compared to the next nearest solar-type star, Tau Ceti. What that means in practice is that the candidate planet at Alpha Centauri A, if confirmed, would be far more accessible to spectroscopic characterization than any other directly imaged planet ever discovered. Its proximity amplifies everything. The same observations that would be marginal for a planet 40 light-years away become tractable for a planet 4 light-years away. The physics of photon collection favors the nearest targets by large factors. If the candidate is confirmed and spectroscopic observations are obtained, the first detections attempted would likely look for the presence or absence of ammonia, which has a strong absorption feature at 10.65 micrometers, directly in the range where Webb's MIRI coronagraph operates. Methane, water vapor at different pressure levels in the atmosphere, carbon dioxide. Each of these molecules tells a different story about the planet's thermal structure, its atmospheric circulation, its bulk composition. A Saturn-like planet with heavy ammonia absorption looks different from one where the upper atmosphere has been chemically depleted through photochemistry driven by the star's ultraviolet radiation. A planet with rings would show a characteristic excess brightness at certain wavelengths. A planet with moons, if those moons are massive enough, might produce a detectable astrometric wobble in the planet's position over time. These observations are not guaranteed. They depend on confirming the planet first, then finding it at a favorable orbital position, then accumulating enough photons over long exposures to extract a meaningful spectrum from what is, even for Webb, an extraordinarily faint source. The timescales are uncertain. The technical challenges are real, but the pathway exists. The instrument exists. The target, if confirmed, exists at a distance that makes these observations more feasible than for any other comparably interesting object in the night sky. And here is a question that has been building throughout this entire story, a question that the data have been leading toward without quite arriving at. What if the 2019 VLT detection and the 2024 Webb detection are not the same object? That possibility cannot be dismissed. The two candidates, C1 and S1, appeared at different positions in the image, at different angular separations from the star, at different apparent brightnesses. The combined orbital analysis treats them as potentially the same object at different points in its orbit. But two separate objects, two planets, is also a scenario that the data do not rule out. In planetary systems, planets tend to come in multiples. In our solar system, the count is 8. Around Proxima Centauri, there are at least 2 confirmed and possibly 3. The occurrence rate statistics from Kepler suggest that systems with one detectable planet typically have additional planets too small or too poorly positioned to be found in the same survey. The phrase that captures this is worth quoting directly. In the researcher Pete Klupar's words, "Once we find one planet, we tend to find others." If the Alpha Centauri A system harbors 2 or more giant planets, in addition to whatever rocky planets might exist in the inner system, the implications for the system's dynamical history multiply rapidly. 2 gas giants in a binary system would generate complex gravitational resonances. They would have sculpted the distribution of any smaller bodies, asteroids, comets, rocky protoplanets, through their gravitational influence over 5 billion years. The inner region of the system, within roughly 1 astronomical unit, might have been cleared of rocky debris by repeated dynamical interactions. Or the gas giants might have shepherded rocky material into stable orbits. The architecture of the system would tell a story of billions of years of sculpting, a story that no current data can yet read. Some researchers are cautious about even entertaining the 2-planet scenario before the 1-planet scenario is confirmed. Others argue that science proceeds precisely by entertaining multiple hypotheses simultaneously and designing observations to distinguish between them. Both positions are defensible. Both reflect genuine scientific reasoning. What is undeniable is that the Alpha Centauri system, long a target of aspiration and frustration, has entered a new phase of observational accessibility. For the first time, a space-based instrument with the sensitivity and wavelength coverage required to directly detect planets in the habitable zones of these stars is actually doing so, or at minimum, producing results that demand follow-up observations at the highest priority. The system has stopped being merely a philosophical target. It has become a concrete scientific problem with specific data, specific candidates, specific orbital predictions, and a specific timeline for the observations that will test those predictions. That shift, from aspiration to concrete scientific problem, is itself a kind of milestone. It is not the end of the story, But it is the beginning of the story's most interesting chapter. The chapter where the data start to accumulate fast enough that the picture clarifies, where each new observation narrows the possibilities, where the universe either confirms what the models suggest or, in its characteristic way, does something unexpected instead. And the unexpected in astronomy is never far away. Stand on a hilltop in the southern hemisphere on a moonless night. Stand somewhere away from city lights, perhaps in the high Chilean Atacama, or on the rocky plateau of the South African Karoo, or on the dark coastal cliffs of Western Australia, where the Milky Way is not a faint smear, but a structural feature of the sky, a river of light arching from horizon to horizon. Look south and slightly east. Find the brilliant pairing of Alpha and Beta Centauri, the two pointer stars that ancient sailors used to locate the Southern Cross. The brighter of the two, the one on the right, burning with a yellowish warmth, is what you are looking for. That is Alpha Centauri. That is where this story lives. From where you stand, the light entering your eye left that system 4 years and 4 months ago. It departed before this discovery was made, before the Webb Telescope pointed its coronagraph at that precise location in the sky, before the orbital simulations were run, before the papers were accepted and the headlines were written. The light you are receiving right now carries no knowledge of any of this. It is just energy, photons streaming across the void, indifferent to the questions they have provoked. That gap between the light's departure and your reception of it is one of the most quietly affecting realities in all of observational astronomy. When you look at Alpha Centauri, you are not seeing it as it is. You are seeing it as it was. That world, if it exists, that Saturn-mass gas giant drifting in its elliptical path around the brighter of those two suns, is right now somewhere in its orbit that you cannot know from the 2024 data alone. It may be near its farthest point from the star, bathed in gentle infrared warmth, its cloud tops swirling with ammonia crystals. It may have swung back toward the closest approach, hidden from Webb's view behind the stellar halo. You cannot know. The orbital simulations give probabilities, not certainties. The planet, if real, is doing whatever it is doing, following whatever gravitational path it has followed for the past 5 billion years, utterly unaware of being observed. That indifference of the cosmos, the fact that none of this searching, none of this wondering makes the slightest difference to the stars and planets themselves, is one of the things that makes astronomy simultaneously humbling and ennobling. The stars do not know they are being watched. The candidate planet does not know it is a candidate. It does not know that a species on a small rocky world, 4 light years away, has spent a century building instruments specifically to detect it, has sent a gold foil-covered telescope to a gravitationally stable point 1.5 million kilometers from Earth, has designed a custom observing sequence for a target that no standard software protocol could handle, and has sat with the ambiguous result: 1 detection, 2 non-detections, and tried with characteristic human stubbornness to extract meaning from it. That stubbornness is worth pausing on. It is not mere ego, though ego is certainly part of science. It is something older and stranger, an orientation toward the universe that refuses to accept the limits of current instruments as permanent limits, that insists on asking questions even when the tools available are inadequate for clean answers, that treats every partial measurement as the beginning of something, rather than the end of nothing. Consider what it took to produce the August 2024 image. The James Webb Space Telescope was launched on December 25, 2021, from the Guiana Space Center in Kourou, French Guiana, on the northeastern coast of South America, as close to the equator as possible to maximize the efficiency of the rocket launch. It traveled to the second Lagrange point, L2, a gravitationally balanced location 1.5 million kilometers from Earth in the anti-sunward direction, where the combined gravitational pulls of the Earth and Sun keep it in a quasi-stable orbit. It cooled to operating temperature. Its infrared detectors require a temperature of less than 7 Kelvin, roughly 7 degrees above absolute zero, to function properly, over the course of several months. Its mirrors were aligned with micrometer precision, using actuators that make tiny adjustments measured in nanometers. And then, for the Alpha Centauri observation, all of that engineering achievement was pointed at a target so bright, so close, and so dynamically complex that none of the standard operating procedures applied. A custom sequence had to be developed from scratch. The coronagraphic mask had to be positioned precisely over the disk of Alpha Centauri A, while the star moved measurably across the sky. The residual light from Alpha Centauri B, itself a brilliant star, had to be modeled and subtracted from the field of view. The result of all this effort was an image containing, somewhere in its processed, background-subtracted, algorithm-cleaned data, a point source 10,000 times fainter than the star being masked. A faint, warm glow, a suggestion of a world. There are moments in the history of science when the gap between the instrument and the object being measured is so extreme. When the thing being detected is so faint compared to the noise, when the margin between signal and artifact is so narrow, that the achievement of even a marginal detection represents something profound about the species doing the detecting. This is one of those moments. Not because the detection is confirmed, it is not, but because it exists at all. Because human ingenuity has been refined to the point where a faint infrared shimmer 4 light-years away in the shadow of a star 10,000 times brighter can produce a consistent signal across 2 independent observational datasets spanning 6 years. This is what the cooling valley of thought looks like when you step back from the technical details and allow yourself to feel the full weight of what the story contains. It is not just a story about a candidate planet. It is a story about what happens when a species that evolved on one small rock decides, collectively and over many generations, to find out whether there are other rocks, or more particularly, other worlds, in the nearest possible neighborhood. The history of that ambition runs deeper than the history of telescopes. It runs back to ancient Greek philosophers, Democritus and Epicurus, who argued for the plurality of worlds on purely philosophical grounds, without any instrumental evidence whatsoever. They reasoned that if the universe is infinite and matter is distributed through it, then other worlds must exist, because there is no logical reason for this one to be unique. Their argument was not scientific in the modern sense. It was an exercise in logical consistency, but it planted a seed. That seed grew slowly. Nicholas Copernicus, in 1543 from his post as a canon at Frombork Cathedral in Poland, displaced Earth from the center of the solar system, making it one world among several. Giordano Bruno, burned at the stake in Rome in 1600, extended the Copernican model to argue that other stars are other suns, and that other suns have other planets. His argument was again philosophical. He had no instruments to support it, but the direction of travel was clear. Each step away from geocentrism was also a step toward the plurality of worlds. Galileo Galilei turned his telescope skyward in 1609 in Padua, Italy, and by January 1610 had discovered moons orbiting Jupiter, the first direct demonstration that not everything in the cosmos circles Earth. In discovering those 4 moons, Io, Europa, Ganymede, and Callisto, he provided the first concrete evidence that complex orbital systems exist beyond our own. the implications were not lost on subsequent thinkers. If Jupiter has moons, perhaps other stars have planets. The conceptual distance from Galileo's moons to the Alpha Centauri candidate is, in one sense, enormous. 4 centuries of instrument development, theoretical refinement, and expanding observational reach. In another sense, it is a single continuous arc of inquiry, driven by the same fundamental question: are we alone in having a world to stand on? Anaphora can trace that arc. It was asked by the ancient Greeks without instruments. It was asked by Renaissance philosophers without evidence. It was asked by 19th century astronomers without the sensitivity to detect planetary signals. It was asked by 20th century engineers who built the first spectrographs, sensitive enough to detect stellar wobbles. It is being asked now in the 21st century by teams using infrared coronagraphs in space, processing images with algorithms that did not exist a decade ago, simulating millions of orbits on computers that would have seemed magical to the astronomers who first pointed telescopes at these stars. The question has not changed. The tools have. The tools have changed so dramatically, so repeatedly, and so rapidly in the past 3 decades that what was once the limit of imagination, direct imaging of a planet around the nearest sun-like star, has become the subject of papers in the astrophysical journal Letters. Accepted papers, reviewed papers, science. Picture yourself not on a Chilean hilltop now, but in a seminar room, in a university somewhere, perhaps Caltech in Pasadena, California, where PhD student Aniket Sanghi works. A room with a projector and a whiteboard and a coffee machine in the corner that has been running since 7 in the morning. On the screen is a 3-panel image. The first panel shows the Alpha Centauri system as seen by the digitized sky survey. 2 brilliant merged dots in the center of a field of fainter stars. The second panel shows the system with Webb's coronagraphic mask placed over Alpha Centauri A, blocking its glare. But the mask's edges produce diffraction rings, circular patterns of light bending around the obstacle, and Alpha Centauri B's halo spreads across the field. The third panel shows the image after the known patterns have been subtracted, the diffraction rings modeled and removed, B's light carefully peeled away. And in the residual cleaned image, at approximately the 2 o'clock position relative to the masked star, there is a small, faint circular smudge, S1. That smudge is the center of this entire story. That smudge represents the best answer currently available to a question that humanity has been asking, in one form or another, for 2.5 millennia. Is there a world around the nearest sun? And the answer, held carefully in both hands and examined from every angle, is possibly, probably. The evidence is compelling enough to drive follow-up observations at the highest priority. Not certainly, not confirmed, but possibly real in a way that cannot be dismissed, in a way that demands the most serious scientific attention available. Now something happens when you sit with that possibly for long enough. It begins to feel less like a limitation and more like an invitation. The uncertainty is not a gap in knowledge to be ashamed of. It is the precise location where the next observation will be aimed. It marks, with unusual precision, exactly where science needs to go next. Astronomers rarely talk about the emotional texture of working at the frontier of detection. The culture of the field, like most scientific cultures, prizes restraint, rigor, and careful language. But the careful language in these papers contains something that careful language cannot fully contain. Charles Beichmann of NASA's Exoplanet Science Institute and JPL, describing the observations as incredibly challenging and saying that the operations team had to come up with a custom observing sequence just for this target, and their extra effort paid off spectacularly, is not merely describing a technical achievement. He is describing a moment when human ingenuity pushed against a physical limit and found something on the other side. Aniket Sanghi, the PhD student at Caltech, who is co-first author on both papers, described being faced with the case of a disappearing planet, language that carries a kind of wonder within its scientific precision. A disappearing planet, not a missing planet, not an undetected planet, a disappearing one, as if it were actively evading detection, moving through its orbit with a quality that has, in human description, the quality of will. The planet does not, of course, have will, but the language captures something true about the experience of searching for it, the sense of a presence that is there and not there, glimpsed and lost, seen in one image and absent in the next. That experience of partial knowledge, of something glimpsed at the edge of detectability, is profoundly and specifically human. Electrons do not wander. Spectrographs do not reach. Only the species that built the spectrograph and aimed it and processed its output and sat with the ambiguous result and ran the simulations and wrote the papers and presented them at conferences and waited for the next observing window. Only that species has this particular experience of being almost certain about something and needing to be more certain and not yet being able to be. This is worth pausing on because it is the thing that makes the Alpha Centauri story more than a technical narrative. It is a story about a species in the act of extending its senses across impossible distances and finding, at the edge of what those extended senses can resolve, something that might be a world. Something that might mean that the nearest address in the cosmic neighborhood is not empty. Something that might, one day, when the orbital period completes, when Webb points again at exactly the right time, when the simulations have narrowed the uncertainty sufficiently, something that might become certain. The future observations are already being planned. The best predicted window for detecting S1 again, based on the orbital solutions derived from the combined 2019 and 2024 data, is fall 2025 and into 2026, when the planet, in the most likely orbital scenarios, would be near its greatest angular separation from Alpha Centauri A, and therefore most detectable above the stellar halo. Whether those observations have been approved, whether they have been executed, whether they have produced a result, these questions exist in the space between what this story can tell you and what the universe has already decided in its indifferent way to reveal or withhold. What we can say is that the prediction exists. The orbital models are specific enough to tell observers not just where to look, but when to look. That kind of predictive specificity is a hallmark of mature scientific reasoning, the ability to make a falsifiable prediction from incomplete data and then design an observation to test it. If the planet appears where the models say it should, in the window the models identify, the case for its existence becomes substantially stronger. If it does not appear in that window, the models must be revised, perhaps toward a different orbital solution, perhaps toward a different interpretation of the original data. Either way, knowledge advances. And here is the deeper truth that the technical story has been leading toward, the thing that becomes visible only when you stand far enough back to see the entire arc of what has happened at Alpha Centauri over the past century. The search for planets around the nearest sun-like stars is not primarily a scientific project. It is a philosophical one, pursued by scientific means. The question driving it is not, at its core, what is the mass of the object at 2 astronomical units from Alpha Centauri A? That is the question that papers answer, And it is an important question, but it is not the animating one. The animating question is older and stranger and more personal. It is the question of whether our situation, a world around a star, with chemistry and time enough for complexity to emerge, is particular to us or general to the universe. Whether what happened here happens elsewhere. Whether the cosmos is unpopulated or empty. Whether the light from those other suns illuminates something or merely travels. The candidate at Alpha Centauri A does not answer that question. Even if confirmed, a Saturn-mass gas giant in a habitable zone orbit around a sun-like star does not directly tell us whether life exists in the Alpha Centauri system. It tells us that the system has at least one gas giant, which tells us something about its formation history, which places constraints on whether smaller, rockier worlds in more stably circular orbits might also exist. It is one piece of a puzzle whose final picture we cannot yet see. But one piece is not nothing. One piece is, in fact, everything. Because the puzzle has no pieces at all until someone builds the instruments, does the work, runs the simulations, and publishes the papers. Every piece came from somewhere. Every confirmed exoplanet in the current catalogue of roughly 5,700 confirmed worlds began as a smudge in a data stream, a wobble in a radial velocity curve, a dimming in a light curve, something small and ambiguous that required interpretation. S1 is currently at that stage. It is in the interpretive phase, the uncertain phase, the phase that science must pass through before it can produce knowledge. The phase does not last forever. Take a moment to look back at the path we have traveled. We began with a single point of light in the southern sky, a light that is actually 3 stars, 2 of them sun-like and older than our own, bound in a gravitational embrace that has endured for 5 billion years. We traced the long history of searching for planets around those stars, the decades of radial velocity monitoring that could not reach the right sensitivity, the ghost planet of 2012 that dissolved under closer scrutiny, the tantalizing hint from the Very Large Telescope in the Atacama Desert in 2019, and the slow accumulation of evidence that something at Alpha Centauri A might be real. We examined how the James Webb Space Telescope, a gold-mirrored engineering achievement cooling at 7 degrees above absolute zero, 1.5 million kilometers from Earth, pointed its mid-infrared instrument at a star too bright for standard procedures, used a custom observing sequence designed from scratch for this single target, and in August 2024 found a point source 10,000 times fainter than its host star, sitting at approximately 2 astronomical units, glowing in the infrared with the warmth of what the best current models say is a gas giant roughly the mass of Saturn. We traced the mystery of disappearance, the February and April 2025 non-detections that seemed at first to undermine the case and turned out instead to be predicted by roughly half the orbital solutions consistent with the combined dataset. We explored what a Saturn-mass world in a habitable zone orbit of a binary star means for planetary formation theory, for the possibility of moons, for the question of what the nearest sun-like star harbors. We sat with the uncertainty, the honest, careful, scientifically rigorous uncertainty of a result that is compelling but not yet confirmed. And we recognized that uncertainty not as a failure, but as a precise address, marking exactly where the next observation needs to go. We examined the history of the question itself, the Greek philosophers who reasoned toward other worlds without instruments, the Renaissance thinkers who paid with their lives for extending the Copernican vision, the 19th century astronomers who mapped the distance to Alpha Centauri for the first time, the 20th century engineers who built the spectrographs sensitive enough to detect planetary wobbles. And the 21st century scientists, Aniket Sanghi and Charles Beichmann among them, who combined all of that inheritance with the most powerful telescope humanity has ever placed in space, and found, or possibly found, something. That lineage, from Democritus to Galileo, to Queloz and Mayer, to Anglada Escudé, to Beichmann and Sanghi, is not a sequence of disconnected individuals. It is a single, continuous act of attention, distributed across centuries and civilizations, directed at the same enduring question. Are there worlds out there? Are we alone in having a world to stand on? The Alpha Centauri candidate does not answer that question, but it changes the texture of asking it. For most of human history, the question was asked into an abyss, directed at stars so remote, so featureless from Earth's surface, that asking it felt like shouting into the dark. Now the question has a specific address. It has a candidate world. It has orbital parameters. It has a predicted detection window. The abyss has a particular location within it that has been illuminated, however faintly and uncertainly, by the most refined instruments a technological civilization has ever produced. That is a different kind of asking. It is asking that has begun to receive an answer. The answer so far is possibly, but possibly in this context is profound, because it means that the nearest sun-like star, the star whose light you can see with your own eyes, the star that has been burning for 1 billion years longer than our own, the star around which ancient light has been circling in patient ellipses since before the first animals crawled onto land on Earth. That star may not be alone. It may have a companion in orbit. It may be, in the precise and literal sense, a solar system, not like ours in every detail. A gas giant where we would want a rocky world. An eccentric orbit where we would prefer a circular one. A binary companion that perturbs and shapes every orbit in the system in ways our sun, traveling alone through the galaxy, does not impose on its planets. But a solar system nonetheless, a star with a world or worlds gravitationally bound to it, moving in the darkness around it, reflecting and emitting light that a space telescope 4 light-years away can, just barely, detect. The physical objects at the center of this story, the star, the candidate, the infrared point source, will continue doing what they do regardless of whether anyone is watching. Alpha Centauri A will burn through its hydrogen for another 5 billion years or so before expanding into a red giant and slowly collapsing into a white dwarf. The candidate planet, if it exists, will continue its elliptical orbit, sweeping inward and outward, warmed and cooled by the star it circles, perturbed by the distant gravitational pull of Alpha Centauri B, indifferent to the category of candidate that a civilization 4 light-years away has assigned to it. It was never waiting to be discovered. It was simply there or not there, following the rules of gravity and thermodynamics with the implacable consistency that physical law provides. Discovery is not something that happens to the universe. It is something that happens to the species doing the discovering. The moment of recognition, the moment when a pattern in the noise becomes a point source, when a point source becomes a candidate, when a candidate becomes a confirmed world, that moment belongs entirely to the observers, to the engineers who built the telescope and the coronagraph, to the scientists who designed the observing sequence and processed the images, to the graduate student who ran the orbital simulations and wrote the phrase "disappearing planet" with the kind of quiet wonder that scientific papers rarely allow themselves to express. And to everyone who has looked up at that steady point of light in the southern sky and felt, without being able to say exactly why, that it mattered, that the proximity was significant, that 4 light years is far enough to be humbling and close enough to be personal. Some scientific results change what we know. Others change how we feel about what we know. The best ones do both. The Webb finding at Alpha Centauri A is, at this stage, still in the process of becoming one or the other, or both. The confirmation has not arrived. The papers are careful and measured and explicitly uncertain. But the direction of travel is clear. The instruments exist. The target exists. The next observation window exists. The prediction is in place. What comes next belongs to time, to the orbital mechanics of a possible world completing another arc around its star, to the scheduling of telescope time on an oversubscribed instrument, to the patience of scientists willing to wait for the universe to come around again. Literally, the planet completing enough of its orbit to return to a position where it can be seen. That patience is not passive. It is active and deliberate and hard-won. It is the patience of people who understand that the universe does not operate on human timescales, that the period of a planet at 2 astronomical units from its star is measured in years, not days, that orbital mechanics does not accommodate impatience, and that the only thing to do in the face of that reality is to build better instruments, design more careful observing strategies, run more sophisticated simulations, and wait. The waiting is not empty. The waiting is when the models are refined, when the theory of planetary formation in binary systems is extended and tested, when the spectroscopic capabilities of future instruments are characterized and prepared, when the question of what molecules to look for in the atmosphere of a Saturn analog in the habitable zone of a Sun-like star is worked through with the tools of atmospheric chemistry and radiative transfer modeling. The waiting is full of science, and it is full of something else too, something that does not appear in papers or conference proceedings, but that is present in the seminar rooms and control rooms and late-night conversations between scientists who work on this problem. It is the sense of standing at a threshold, not inside the room beyond, not fully committed to the hallway behind, but right at the door, with data that say something is there, and instruments that can look again, and a prediction that tells you when and where to look, and the quiet certainty that the question will not remain unanswered indefinitely. The nearest Sun-like star, a point source 10,000 times fainter than its host, an elliptical orbit threading the habitable zone, a disappearance predicted by half the simulations, a reappearance expected if the models are right in a window that has already begun. 4 light years of empty space between this moment and that star. Light traveling across that distance right now, carrying no information about the questions it has provoked, arriving at your eye as it has for every human who has ever looked at the southern sky and felt the pull of proximity. The light arrives. It always has. And somewhere in that system, in the gravitationally complex, ancient, sun-like warmth of Alpha Centauri A, something may be orbiting, patient, silent, real. If this changed how you think about the stars overhead, or about the long arc of human searching, or about what it means to be almost certain of something and need to be more certain, then the time was well spent. The universe keeps its secrets at the limit of what instruments can reach. We keep building better instruments. That conversation between the cosmos and its most curious inhabitants is far from over. Thank you for staying with it tonight.